Right, hello and welcome back to another video. Today we are going to be discussing something called pulse width modulation, also referred to as PWM, which is how I will be referring to it for the majority of today's video. Let's start by explaining what PWM is. PWM is a digital technique to control signal by repeatedly toggling between high, that's rubbish, high and low states. So if you have to think of these as the high states and these are the low states in a consistent pattern. Think of PWM like a light switch being turned on and off rapidly. By controlling how long the switch stays on for, we are able to control the brightness of the light, mimicking a dimmer. The signal has two key parameters, duty cycle and frequency. If we look at this graph that we've got here, a very basic graph, but this is the basic idea of what a PWM graph looks like. If we look at the graph, we see that we have a high, also known as an on time, and our low state, also known as an off time. And in order to get the frequency, it's pretty simple. If we were to look at this distance, it would normally be in milliseconds. So let's say 10 milliseconds, which is equals to 10 times 10 to the minus 3 seconds. To get the frequency, you would say that's the period, right? Just to clarify, if we wanted to get the frequency, we'd say frequency. Wow, this is great. This pen isn't working very well, so let's try. We've got blue, so we're going to try that. See if we can get that one to work. Okay, so frequency, as you can see here, is 1 over the period. So if our period is 1 over 1 or 10 times 10 to the minus 3 seconds, we would end up with a value of, I believe, 100 to the second minus 1, which is also equals to 100 hertz. Okay, so now that we've got the frequency, the duty cycle percentage is the percentage of the total period that is taken up by the on time. That is shocking. The on time. So let's say it is, since our period is 10 milliseconds, let's say this is 5.5 milliseconds. The duty cycle percentage would equal to 55%. Again, so in other words, the duty cycle percentage is simply the total percentage of one period that is made up by the high state. Now, how does this apply to the circuits that we've been building? In the flickering LED video, the LED flashes at regular, predictable intervals because of PWM. We set up an A-stable 555 timer circuit which produces a square wave. Its high to low time ratio is what defines the PWM's duty signal cycle. The ratio of these times can be adjusted by changing the values of resistors 1 and 2 and the capacitor. This means that we could easily adjust how the LED behaves when the circuit is fed power. The theory of PWM that we use in this video is largely the same as in the alternating LED video that followed. I really became aware of this mythical beast known as PWM when I was doing research for my Tesla coil part 1 video. My buzzer had arrived and I was able to start testing and prototyping. I had no idea why my simple circuit containing a resistor, a switch, battery and buzzer wasn't, buzzing. So I started reading up to see what was wrong with my buzzer, since I could never be the problem. I found that my buzzer needed pulse width modulation to produce a sound, and my circuit wasn't providing that. So what I did was I rebuilt the flashing LED circuit using the buzzer instead of the LED. And to my relief, it created the most penetratingly annoying sound I'd ever heard. You see, passive buzzers need PWM signals to generate sound, since it allows you to control the frequency and volume of the sound produced. After I spent a while experimenting, trying to get decently reliable outcomes and failing wonderfully, I decided to turn to something much easier and far more expensive. An Arduino, or at least a relatively cheap knockoff. This fancy little piece of kit handled all the PWM nonsense by some magic known only to people who are much smarter than I am. What? Aren't you happy with that explanation? Well, I guess I'll try and make it make sense. While Arduinos do not automatically output PWM, one can use the analog write function to output PWM signals to certain pins at a fixed frequency, which is normally around 490 Hz. And so, to properly answer the question I know you're all begging to be answered, an Arduino can output PWM signals if it is coded to do so. Finally, we get on to our latest video, the servo motor, which received a comment on PWM, inspiring me to make this video, so thank you very much for that. A servo motor's electronic board measures the width of the on-time pulse in the PWM signal. The servo motor then uses this information to maintain its target position, which likely explains the shaking that we experienced. This shaking can occur if the PWM signal is noisy, or if the servo struggles to maintain its target position due to slight mismatches in pulse timing. I know this has been a bit of a different video. I thought I would try and learn something about PWM since it has cropped up a couple of times, and I thought maybe you guys would like this. Hopefully explain why some of the circuits have actually worked the way that they have, rather than just say it's because you plug in certain components and that's what they're meant to do. So I hope you enjoyed it, and I look forward to seeing you in the next one. Cheers.